Alright, quick shameless plug for my website. There it is. In this video we're going to talk about finding max and mins using Lagrange multipliers. So the basic idea is you're again trying to find a maximum or minimum of a function. I wrote it generically depending on 3 variables. My actual first example I'm just going to use 2, but the idea is going to be the same. It's going to be subject to another equation involving x, y, and z that's going to equal some number, and this is what's called your constraint. So we'll make some more sense out of this, I think, in our actual concrete example. The basic idea, and you can do this stuff if you've seen gradient notation and things like that, you can use all that, but I'm going to do it, I mean it's equivalent, I'm going to do it without it though. So what you do is you form a new function that depends on x, y, z and the symbol lambda, and to get that new function you just take whatever you're trying to maximize or minimize and you subtract away the original constraint. You set it equal to 0 though, and then you also multiply that by lambda. So that's how you come up with this new function. And then you basically, this new function, you take partial derivatives of that with respect to x, y, z, and lambda, whatever your variables are. Set it equal to 0. This is going to be the tricky part usually because you're going to get a big system of equations that you have to solve, and in general there's just no procedure to solve a generic system of equations. If they're linear you can use matrices, things like that, but in general that will not happen. And then once you get your solutions from the system you just plug them back into your original function, and that's either going to give you a maximum or a minimum. Alright, so let's do a concrete example here to make some sense out of this. So just kind of a little bit of a word problem to put it in context, I guess. So suppose you make TV sets at 2 different factories. We'll call them factory A and factory B. Suppose you're making portable TVs and plasma TVs. Who cares? Suppose you make X TVs at factory A, Y TVs at factory B, and the cost given by the production of X TVs and Y TVs is this function 6x squared plus 12y squared. Now suppose you have to produce 90 TV sets a month, and what you're trying to do is figure out, well, how many of X should you produce and how many of Y should you produce so that you meet that requirement of exactly 90 TV sets. But obviously in this case you're going to want to keep your costs at a minimum, okay? Unless you're a bad business guy or gal. We'll assume though we're not, because hey, we're smart people and we're taking calculus, so probably want to minimize this function. Okay, so what I'm going to do on this again is I'm basically going to do like I said in the last part. You take whatever function you're trying to maximize or minimize, and then you subtract away lambda times your constraint. And notice in this case our constraint, since we have to produce 90 TV sets, our constraint would be that, well, the number of TV sets from factory A plus the number of TV sets from factory B, turn on some light here, sorry about that, that would have to equal, well, 90. What you do with this constraint again though is you want to make one side equal to 0. So I'm going to write this as x plus y minus 90, and now I'll have 0 on the right side. And in this case this is my function, well, it's not in terms of x, y, and z, but it is in terms of x, y, and the symbol lambda. Okay. So what I get to do now is I should take partial derivatives of all of this. So maybe I'll just multiply it out first to make it a little clearer. So I'll get minus lambda x minus lambda y plus 90 times lambda. Okay, and now I'm going to take partial derivatives. So the partial derivative with respect to x, remember we're treating now y and lambda as constants. I'll get 12x, my 12y squared will go away, I'll get a minus lambda, and then everything else will disappear. If I take the partial derivative with respect to y, I'll get 24y minus lambda, everything else will disappear. And then if I take the partial derivative, whoops, I almost wrote a z, with respect to lambda, the x squared, the y squareds will disappear. It looks like I'm going to get a minus x term, a minus y term, plus 90. Okay, so now what we have to do is we actually set each of these equal to 0 and we solve. Okay, so if I set this first one equal to 0, if I solve this for x, notice I could add lambda to both sides and get that x equals lambda over 12. If I do that to the middle one as well, I'll add lambda to both sides and divide by 24, and I'll get that y equals lambda over 24. Now what I'm going to do is I'm going to take these two things and plug it into my other partial derivative. Okay, and what this is going to allow me to do is it'll allow me to solve for lambda. I'll then be able to go back and figure out values for x and y. Okay, so if I plug in that x is negative, well, it's negative lambda over 12 minus lambda over 24 plus 90 equals 0. And now on the left side, you could simply get common denominators, multiply top and bottom of the first one by 2. On top, you would get negative 3 lambda over 24. I'm going to subtract the 90 and get negative 90 on the right side. If you divide both sides by negative 3, we'll get that lambda over 24 equals, looks like positive 30 to me. Whoops, squeeze it in there. And multiply both sides by 24, and you'll get that lambda equals 720. Alright, so now at this point, I'm going to plug lambda back into my x and y values, because after all, I'm trying to find values for x and y that maximize or minimize. So if I plug that back in, I'm going to get that x equals lambda, which is 720 over 12. I'll get that y equals, okay, that was lambda over 24, so I'll get 720 over 24. And you can simplify both of these down. It looks to me like x should equal 60, y should equal 30. Okay. Typically, once you have values for x and y, you may find more than one pair that works. Here we're only finding a single pair, 60, 30. And what you need to do is you need to plug those back into the original equation. And so the thing you're trying to minimize or maximize, in this case we're trying to minimize this cost function, 6x squared plus 12y squared. Well, the cost of making 60 TV sets times 30 and 30 of the other TV sets will be 6 times 60 squared plus 12 times 30 squared. And to justify that at this point this either has to be a maximum or a minimum. If you wanted to justify that it's a minimum cost, you could also take just some other random point. Maybe you make 61 of the other TV sets from factory A, which means you only make 29 from factory B. Plug that in to this cost equation, and you'll see that the value you get out when you plug in 61 and 29, you'll actually find out that this cost is greater than the cost we found up here when you plug in 60 and 30. So since you can actually make the cost greater, that in fact now justifies that, well, it was either a maximum or a minimum. Well, we can make it bigger, so okay, we've now reduced it to the fact that this must be a minimum. Okay, so this is the basic idea with Lagrange multipliers. The only thing that's going to be trickier again is if you have more variables floating around. You're going to get more partial derivatives. You're going to have more variables floating around your equations more than likely. And again, solving the system of equations to me turns out to be the tricky part in general. So this one wasn't so bad. I was trying to take a straightforward example. But sometimes you have to be pretty clever, and definitely there's times where I look at them and get stuck myself. So this is the tricky part. Again, whatever values you find for x and y, you should plug those back into your whatever you're trying to maximize or minimize, and then just justify that that is a maximum or a minimum. So again, you can do this stuff using gradient notation and some other notation. I prefer this notation myself, but you know, use whatever you're comfortable with. I'm going to do another one as well using x, y's, and z's, so take a look for that. Hope this helps. If you have any questions, shoot me an email. I'll be happy to get to them as soon as I can.